Hey everyone, this is question number 25 from chapter 5. So this problem is about a race car that accelerates uniformly from rest to 270 kilometers an hour in a semicircular arc with a radius of 220 meters. The first part says to determine the tangential and radial acceleration of the car when it is halfway through the arc. So the tangential acceleration is what actually causes the speed to change. And we can solve that using equation from the textbook. Using equation 2-11c, which says v tan squared minus v naught squared tan equals 2a acceleration tangential times delta x tangential. So we can rearrange this and solve for a tan equals v squared tan minus v naught squared tan over 2 delta x tan. So now we need to figure out what all this is. We know initial velocity is 0. Final velocity, I went ahead and converted to meters per second up here just by dividing 270 kilometers an hour by 3.6, which is the conversion factor. So I went ahead and changed that. And then we need to figure out what this delta x tan is. So for tangentially, if we're traveling a semicircle, it's going to be 1/2 of the circumference. So 1/2, which would normally be 2 pi r. So that's going to cancel, so it's just going to be pi r. So now let's go ahead and plug in our values. So 75 meters per second squared divided by 2 times r, 220 meters, times pi. And that gives us a tangential acceleration of 4.069 meters per second squared, which we can equate to 4.1 meters per second squared. Okay, so that's tangential acceleration. And now we go on to, with the tangential, we can find the speed that the car has halfway through the turn, and then calculate the radial acceleration from there. Okay, so we can find speed halfway through the turn with equation 211 again, 211. So we have v squared tan minus v naught squared tan equals 2a tan delta x tan. So now we v naught is 0. Take the we can't say that v naught is 0. We solve for v tan. We can say it we'll end up taking it out using it. So we solve for v, which is vf tan, add over to the other side, this over to the other side, and then take the square root. So v tan is equal to the square root of v naught squared tan plus 2a tan delta x tan. So now this is where we can go ahead and take out v naught. We should keep it in as long as we can. So v tan is equal to the square root of 2. We just solve for a, 4.069 times delta x tan halfway through the circle, that's going to be half of the radius, so 110 pi meters. Plug that in and you get 53.03 meters per second. Okay, so this is the speed halfway through the circle, and now we can solve for the radial acceleration. So AR equals, we know this equation well, v squared over r. Okay, so now this is equal to 53.03 meters per second squared. The square's on the outside. Meters per second squared over r 220 meters. And that gives us a radial acceleration of 12.78 meters per second squared, which we can equate to 13 meters per second squared. And that is AR. Okay, so now the second part of this question asks us to find the static friction if there was no bank, if the road was flat. So the total acceleration is given by the Pythagorean theorem of the tangential and centripetal acceleration. So A total equals the square root of AR squared plus A tan squared if static friction is to provide the total acceleration, then friction is going to have to equal MA total. We assume that the car is on the verge of slipping and is on a level surface, so the static friction force has its maximum value of F equals mu s Fn, which Fn we know is mg. If we equate these two expressions for the frictional force, we can solve for the coefficient of static friction. So let me write out what I just explained. So the friction is responsible for providing the acceleration. So we have F is equal to MA total. Okay, so that has to be equal to each other. So then we have mu s mg is equal to m, this expression that we just wrote out for the total acceleration, AR squared plus A tan squared. So now we solve for mu s and we plug in our values. Excuse me. All right, so mu s equals square root AR squared plus A squared tan over G. Masses are going to cancel. So plug in our values. Mu s equals A squared AR squared 12.78 meters per second squared plus 4.069 meters per second squared over gravity 9.8 meters per second squared. Plug that into your calculator and you get mu s equals 1.37, which we approximate to 1.4.